In this second problem, we actually have a bullet being fired and embedded in a block. So here's the situation. We have a bullet moving like this. So that means its speed is bigger than 0. And since its height doesn't change, essentially, we're going to say that the height of the bullet is our 0 height mark, and anything below that is negative height, and anything above that is positive height. And the other thing is we have no spring, so there's no elastic energy to contend with. Now what's going to end up happening is that we have a block, and what's going to happen is that this bullet is going to kind of penetrate the block and be embedded in the block like this. So what does this tell us? The speed of the bullet ends up being 0. The height of the bullet is still 0. We don't have any spring energy, but we do have dissipated energy as some kind of, we can call it a friction force in the block dissipates all the energy of the bullet, and then the energy is stored as internal energy, heat, in the block. So let's actually talk about what the bar graphs look like and then worry about what they're actually asking us. So here's what they're asking us. They want to know how far deep the bullet goes into the block. So they want to know this x here. Now if you notice, they give us a force F. So I'm going to tell you right now, we need to deal with the work idea. So work, I'll give it like a Wonder Woman W, work, is going to be force times the distance we move through. And so in this case, we are going to actually set up kinetic energy bar graph and dissipated energy bar graph. And we begin this problem the way we do all other problems, which is using our energy bar graph. So 1/2 times 0.02 times 350 squared equals the dissipated energy. And when we actually calculate out that number, double check this on your calculator. I might have this wrong. I have the E dissipated as 1,205 newtons, and I'm just going to write check my number to make sure I got that right. Okay, so that's the dissipated energy, and sorry, that should be joules, not newtons, because it's energy. Now here's where the work idea takes over. So in order to convert this kinetic energy into dissipated energy, we needed work done to do that, because if you remember from our notes, work is how we convert energy. And what we're saying in this case is that the friction force is the force that makes all this energy dissipated. So we're going to say the work done is what gives us our dissipated energy. That's the fundamental idea. So we have, now we just use our formula, F times X is E dissipated, where E dissipated is 1,205 joules. And the force that we apply is 50,000 newtons. And when we actually, times x, so that's force times x is 1,205 joules. When we actually isolate the distance that the bullet goes into the box, we end up getting about 0.025 meters. So that kind of highlights a little bit of what we're going to be doing with forces when we look at the idea of work.